Welcome to our second recorded lecture. Today we're going to cover section 4.8. It is a continuation of what I started last time, which was about the row space and column space. So please, if you still have not seen the other video about the row space, column space, and null space of matrix, please do it before moving to this section 4.8, which is about the rank and nullity of a given matrix. So I'm going to restart with a simple example, and through the example we're going to review things that we have seen in the previous recorded lecture about the column space, row space, and the null space. So I'm going to take a matrix. Okay, let's say exercise, just from the book I'm picking up matrix exercise 148, page 280. So we have a matrix A that is 3 by 4, so 1, 2, minus 1, 3, 4, minus 3, and 1, 2, 0, 4, 0, 5. I'm gonna find the basis for the row space, the basis for the column space, and the basis for the null space of this matrix. So as I have said in the previous lecture, recorded 1, you have to do write A in row echelon form, apply elementary row operation, and then everything will be clear for you. So I'm gonna say R2 becomes R2 minus 2 times R1, and then we obtain this is 1, 0, and let's do it together, and R3 becomes R3 plus R1. So 0, here I have 3, 4 minus 6 minus 2, minus 3 plus 3 is 0, I have 1, 2 minus 2 is 0, and 0 minus plus 1 is 1, and then I have 4, and here minus 8, and 5 plus 4, it's 9. Okay, so now already I have to stop here. This one is in REF, sorry. So I see I have a pivot here, leading term in the first row, leading term in the second row, leading term in the third row. So I pick up exactly these 3 rows, and I will say R1, which is equal 1, 3, 1, 4, R2, which is equal 0, minus 2, 0, minus 8, R3, which is equal 0, 0, 1, 9. This is a basis for the row space of A, so which I denoted R of A, the row space of A. And now I have 3 pivot again. Pivot in the first column, pivot in the second column, pivot in the third column, but I do not pick up those columns. I go back to the initial one, the corresponding one. I'll take the first column, second column, and third column, and I will say that this form a basis for the column space of A, 1, 2, minus 1, and V2, let's call them V2, it's 3, 4, minus 3, V3, which is equal 1, 2, 0. This is a basis for the column space of A. Okay, so here a very simple observation. You see how I counted the leading terms, which are the pivot, to figure out a basis for the R of A, and also to figure out the basis for the column space of A. Now, if I ask you for the dimension of R of A, obviously it is exactly the number of pivot that I counted, because for each pivot correspond one row, I take exactly that row and I put it as a vector in the basis. So the number of leading terms, what I call them pivot, gives you exactly the dimension of R of A. And it is the same for the column space of A. The number of pivot tells me exactly how many vectors you have in the basis, and that will gives you the dimension. So you will see here through this example that you will have always dimension of the row space equal to the dimension of the column space. The dimension of the row space is equal to the dimension of the column space. In general, the row space has nothing to do with the column space, and I say in general because if you look to the identity matrix, the column space is exactly the row space. But in general, for given matrices, row space and column space are different. So, however, they have always the same dimension. They have always the same dimension, although in general they are different. So here the observation that I'm gonna put, very important, and you keep this in mind all the time, it's important. I don't call it theorem because it's trivial, but it's important information. The dimension of the column space of any given matrix is equal to the dimension of the row space of any given matrix. So dimension of column space is equal to the dimension of the row space. And this is exactly what we call the rank of a given matrix. So I go now directly to the definition of a rank of a given matrix. The rank of A is the dimension of the row space of A. Which is, by the previous, I said, observation, I wrote it here, the dimension of the column space of A. Of A. So this is the first definition of today about the rank. The rank, so is the dimension of the row space, which is exactly equal to the dimension of the column space. Okay? Now, second definition. The nullity of A. Well, the nullity of A will be the dimension of the null space of A. So, the nullity of A is the dimension of the null space of A. Okay, let's for example go back to this example here, this guy here, example, and let's figure out the null space, and we're gonna compute the nullity. That means compute the number of bases, a number of vector in the basis of the null space. Okay, so now what I'm gonna do, I reach here REF, and I'm gonna push a little bit more to REF, reduced row echelon form. So what I'm gonna do, I'm gonna take this here, the second row, I'm gonna divide it by -2. So I'm gonna say R2 becomes -1/2 R2. So I have now 1, 0, 0, 3, 1, 0, and then 1, 0, 1, and then I have 4, -4, and 9. Okay. Then I use the pivot here to make this entry equal to 0. So I'm going to say R1 becomes R1 minus R3. So I got 1, 0, 0, 3, 1, 0, 0, 0, 1, and minus 5, minus 4, 9. This one was 4. Yes. Okay. Now I use this pivot here to make this entry equal to 0. So I'll say R1 becomes R1 minus 3 R2. 1, 0, 0, then 0, 1, 0, then 0, 0, 1, and I have minus 5, minus 12, minus 17, 4, and 9. Now this one in R, R, E, F. So if capital X, that is equal x1, x2, x3, x4 is such that AX is equal the O vector of R3, then the first row gives me that x1 is equal 17 x4. Second row give me x2 is equal minus 4 x4, and the third row gives me x3 is equal minus 9 x4. x4 is 3. Okay, and so I rewrite my capital X is gonna be equal 17 x4 minus x4 minus 9 x4 and x4, which is equal x4 times the vector 17 minus 1 minus 9, 1, and we said x4 in R, and that tells me that the null space is spanned by only one vector, n of A. The null space of A is the span of the vector 17 minus 1 minus 9 and 1, and so the nullity of A, this is the basis for the null space spanned by only one vector, so the null space spanned by only one vector, so that vector form a basis for the null space of A, and so the nullity of A, therefore nullity, this is the notation, nullity of A, we write it like this, is equal exactly 1. Nullity of A is equal to 1. Okay. Let's go to a very important theorem here. But before the theorem, I would like to make the following remark. Okay. So let A be M by N matrix. Let A be a M by N matrix. So we have seen that in the previous video about when we introduced the column space and the row space, we have seen the following. We said that the column space of A is a subspace of Rm, and we said that the row space of A is a subspace of Rn. Okay. Now, if the column space of A is a subspace of Rm, automatically the dimension of the column space, which is the rank of the matrix, will be less or equal to M. And if the row space of A is a subspace of Rn, then also this will give me that the dimension of R of A is less or equal to N. So by definition now we said, right, that what we call the rank is the dimension of the row space, which is equal exactly the dimension of the column space. So this statement here tells me the following: the rank of A is less to both M and N, so it will be less or equal to the minimum between M and N. Okay, so because we have the rank of A is less than N, the rank of A is also less than M, so the rank of A will be less than the minimum of M and N, because it is less than both M and N at the same time. So this is just simple observation, but it's very important that we will do some exercises about this remark. Okay, a second remark. I'd like to go back here because this remark is related to what you have seen in the first chapter number 1. Okay, look to this matrix here. This matrix size is 3 by 4. 3 by 4. Okay, so when solving this system, AX, this homogeneous equation, AX equal to 0, means I have 4 unknowns. This is why I put x1, x2, x3, x4, and I have 3 equations. Okay, every column is associated to one variable for this homogeneous system. Okay, after doing elementary row operation, reaching, for example, REF, it's enough here. I see that I have 1, 2, 3 pivot. Okay, so the number of columns is 4. I have 4 unknowns, and I have 3 leading terms, what I call them pivots, 3 leading terms. So, number 4 unknowns minus the number of the leading terms, that tells you exactly how many free variables you have in your solution. We know we find one free variable. That is from chapter number 1. Number of columns minus the number of the leading terms or the pivot gives you exactly the number of a free variable in your solution. And the number of free variable in your solution gives you exactly the dimension of the null space. Gives you exactly the dimension of the null space. That means the nullity of A. I repeat, the number of columns minus the number of the pivot gives you exactly the number of a free variable in your solution. This is known from chapter number 1. The observation now, the number of variable here in this solution to the homogeneous system AX equals 0 gives you exactly the dimension of the null space. That means the nullity, which is now 1. Okay, now if you sum the number of leading terms, that means pivot, plus the nullity, you get exactly the numbers of columns. I repeat, nullity plus number of leading terms gives you exactly the number of columns of A. So in other words, if I connect everything together, number of leading terms gives me the rank, because exactly this, the number of leading terms is exactly the rank. The number of columns minus the number of the leading terms gives me exactly the dimension of the null space, which is the nullity. So always for any given matrix, the nullity plus the rank equal to the number of columns. Nullity plus the rank equal to numbers of columns. So this is what we are going to write here. Very important. Let A be M by n matrix. Then rank of A plus nullity of A is equal n. This one number of columns of A. Okay. Do not forget the rank is given by number of leading terms, which I call also pivot, in the row echelon form of the matrix. And the nullity is given by n minus the number of pivots. So when you sum them, here you have the number of pivot, here is n minus the number of pivot. You sum them together, you get exactly the number of columns in your matrix. This is extremely very important theorem. You really need to remember this. It's probably most important theorem for this chapter. Okay, so you have to remember this one. It's very important. Many exercises are based on this theorem here. Okay, now let's make a remark about the transpose of a matrix A. Remark. So in the previous recorded lecture about the row space and column space of a given matrix, we have seen that the column space of A is the row space of A transpose, and the row space of A is the column space of A transpose. Okay, so we recall that the column space of A is equal the row space of A transpose, and the row space of A is equal to the column space of A transpose. Okay, now from this you can see that dimension of the column space is going to be equal to the dimension of the row space, or you can read it here, dimension of the row space is equal to the dimension of the column space of A transpose. But that gives you that the rank of A and equal is exactly equal to the rank of A transpose. Okay, because definition of the rank is the dimension of the column space, which is equal exactly the dimension of the row space. But it's going to be equal also the dimension of the column space, which is equal to the dimension of the row space for the transpose. So from here, we can easily deduce, based on this definition that I wrote here, we can easily deduce that the rank of A is always equal to the rank of A transpose. Therefore, I'm going to write the rank of A is equal to rank of A transpose. And this is for any matrix. Okay, so let's then go back and write this equality for the transpose. In this case, I'm going to write this one for the transpose, A transpose. So normally, if I replace A by A transpose, what should I get? I should get the rank of A transpose plus nullity of A transpose is equal not N here, but M. But since rank of A transpose is equal to rank of A, I will obtain another inequality that is the following. Rank of A plus nullity of A transpose is equal to M. Okay, so let's repeat this one. So A is M by N matrix. So A transpose is N by M matrix. Now this, I write this equation, this equality for the A transpose. I have rank of A transpose plus nullity of A transpose is equal to number of columns of the A transpose, which is equal to M. But I know that rank of A is equal to rank of A transpose. So this is gonna give me that rank of A plus nullity of A transpose is equal to M. And here I use this one. I replace the rank of A transpose by rank of A because they are equal to each other. And then you obtain another equality similar to here. It's rank of A plus nullity of A transpose equal to M. Please don't mess up M and N here. Okay, let's do some exercise. Okay, we can erase this part here, this example here. Exercise 162. And the first part A. So it is given A is a 4 by 7 matrix. A is a 4 by 7 matrix. Okay. First question, what is the maximum possible number of leading terms, that mean pivots, in the reduced row echelon form of A? The maximum possible leading terms in the row echelon form of A. So A has how many rows? Has 4 rows. So the maximum possible value for the maximum possible number for pivots you are gonna get leading terms is exactly 4. So I mean in REF, A can have at most 4 leading terms or pivots. Okay. And now, what is the maximum possible number of parameters in the general equation, in the general solution of AX is equal to 0? This is question B. So, what is the maximum? So, what is the maximum possible number of parameters? Parameters means free variable. Free variable. In the general solution of AX is equal 0. In the general solution of AX is equal to 0. A is 4 by 7. That means the X, your X, this guy. This is 4 by 7 matrix. So that means the X is 7 by 1. And this 0 is the 0 of R4. Okay? So in this case, the maximum general, the maximum possible number of free parameters. So when you have a vector columns here, 7 by 1, the maximum number of free variable you could have there is 6. Okay? Or 7. But what does it mean if they are all 7? If you have 7 variables free, what does it mean this? That means the matrix A will be the trivial matrix, which is the 0 matrix. Okay? So 7 is the trivial case. If you have 7 variables, that means your matrix A is the 0 matrix. That means whatever you put X here, it's going to be always a solution. But if you avoid the trivial case, that means if you know in advance that the matrix A is not the 0 matrix, then the maximum value will be 6. But in this exercise, he's not saying anything about the matrix A. So I have to assume that the matrix A could be the 0 matrix. 0, 4 by 7, this one. So all these 4 by 7 entries, they are all 0. They could be, because nothing is mentioned in the exercise. So I have to put my answer is 7. That is the maximum number of free variables in the solution AX is equal 0. But I want you to understand that this limit case 7, I have 7 variables, means now if I obtain exactly 7, that means the matrix A is the 0 matrix. But if I had the information, if he's telling me A is not the 0 matrix, then the maximum value of free variable will be 6, not 7. So I have to write 7, but I want you to understand what is the meaning if it's exactly 7. So the maximum number of free variables or free parameters is 7. 7. And I'm going to put here, it is equal to 7. It is equal to 7 when A is the 0 matrix. Okay. Now let me put a remark here. And I'm going to connect this exercise to this one here. Okay? So what did we say here? We said 4 by 7 matrix. So n is 7. N is 7. And rank of A plus nullity of A is 7. So the nullity of A is n minus the rank of A. If you would like to maximize the nullity, because the nullity is the number of a free variable in this equation AX is equal 0. I repeat, the nullity is the number of free variables. That means what he's asking here. So nullity is equal the number of the free variable in the general solution of AX is equal 0. So you have the nullity is equal n minus the rank. If you would like to maximize the nullity, you need to minimize the rank. And so I have n minus the rank, and n is equal to 7. So to maximize the nullity, I need to make the rank it's equal 0, and then you'll see that the maximum number here will be 7. So just a remark here. I put it as a remark, but you will see the next question will be exactly about this remark. So we have for remark of this exercise, for this question B. So we have in our case, we have rank of A plus nullity of A. This is equal to 7. The number of columns of the matrix equal to 7. So if I write now nullity is going to be 7 minus the rank. So nullity of A is equal 7 minus the rank of A. Now the question, you would like to maximize the nullity because he was asking about the largest number, the maximum number of possible, the maximum number of free variable in the solution Ax is equal 0. And I told you, if you have this equation Ax is equal 0, the number of free variable in this solution is exactly equal to the dimension of the null space. That means equal to the nullity. So if you would like to maximize the nullity, you need to minimize the rank. If you would like to maximize the nullity, you need to minimize the rank because of this sign minus. You have it 7 minus the rank. So for this number to be maximum, this guy has to be minimum. And so when you minimize this, you get it, the minimum value for the rank, you get it 0. And the rank is 0 when A is the 0 matrix. The rank is equal to 0 when A is a 0 matrix, and this is how you obtain that the maximum value for the nullity is equal to 7. And the maximum value for the nullity, because the nullity is the number of free variable in the solution Ax is equal 0, gives you the answer to this previous question. So you could think about it in two ways. Either you think about it like this, or you think about it using this equation here. So I repeat again here, because of the sign minus, if you would like to maximize the nullity, you need to minimize the rank. If you would like to maximize the nullity, you need to minimize the rank. And the rank is equal to 0 for the matrix, for any 0 matrix, square or non-square matrix. The rank is equal to 0. This is why you find that the maximum for the nullity will be 7. That means that is the maximum value for the free variable in the solution of Ax is equal to 0. And I repeat, this is why I wrote for you here the number 7. You attain exactly the number 7 when your matrix A is the 0 matrix. Okay, so let's continue with the exercise. Question number C. Now he's changing the size of the matrix A, and he's telling you that the matrix A is 7 by 4. Now A is 7 by 4 matrix. And the question is, what is the maximum possible number of leading terms in A? So let's do it through this equality here. So the question is, what is the maximum number of leading terms in the row echelon form of A? Okay, leading terms are pivot. Okay, so we know that the number of leading terms exactly gonna give you is gonna give you the rank of the matrix A, the rank of the matrix A. Okay, so we know that the rank of A is equal n in our case is 4 minus the nullity. So it's 4 minus nullity of A. Everything here are integers, greater or equal to 0. Okay. You would like to maximize the rank. The rank is the number of the leading terms in the row echelon form of A. So I need to minimize the nullity. I need to minimize the nullity. I would like for the rank, I need to maximize this. That means I need to minimize the nullity. Okay, so this is the number of pivots. That means leading terms in REF, in row echelon 4. Because of this sign minus, to maximize this, you need to minimize this guy. And the minimum value for the nullity is 0. The minimum value for nullity of A is 0. And you obtain 0 when you have only the trivial solution. That means the only solution to AX is equal to 0 is X is equal to 0. So you want to maximize this. That means you need to minimize the nullity. So the minimum value for the nullity is 0. So the maximum value for the rank is going to be 4. So that means that will be the answer to this question. The maximum number of pivot leading terms means in the row echelon form of the matrix A is 4. So my answer here will be 4. Okay. Another remark here, because it's good to think about those answers in different way. Another remark here. Okay. The size of the matrix is 7 by 4. 7 by 4. Okay, that means each row, we have 7 rows and 4 columns. 7 rows and 4 columns. But each row is in R4. Each row is in R4. And we know that the row space of any given matrix is a subspace of Rn. So if I write exactly this line for the given example, I know my matrix is 7 by 4. So the row space of A is a subspace of R4. The row space of this given matrix is a subspace of R4. And so the dimension of the row space, which is the column space, which is the rank of the matrix A, the dimension of the row space is exactly by definition the rank of A. At most is equal to n, that means 4. At most is equal to 4. So the maximum value of the rank is 4. The maximum value of the rank, if I take just this remark here and apply to this given matrix, I will see that the rank, this is the rank of the matrix. Rank is at most 4. So the rank of A is at most 4, and so the rank, as I said before in the beginning of this video, I told you that the rank is exactly the number of leading terms when you have the row echelon form of the matrix or the reduced row echelon form of the matrix. So this is why the answer to this one, what is the maximum number of leading terms in REF of A, is 4. Okay, so you see, this is why I'm telling you that this guy is very important. Our case, the rank of A is less than the minimum between 7 and 4, 7 and 4. But the minimum between 7 and 4 is exactly equal to 4. So this is why rank of A will be less or equal to 4. So let me write it here. In our case here, rank, or let's use another color. Rank of A is less or equal to the minimum between 7 and 4, which is equal 4. The minimum between 7 and 4 is 4. So I have rank of A is less or equal, so let's write it like this, less or equal to 4. And this is the minimum between 7 and 4 is equal exactly to 4. So I got rank of A less or equal to 4. This is why the maximum number of leading terms in the row echelon form of A is 4. Okay, D, last question here. So again, A is 7 by 4 matrix. And the question is, what is the maximum possible number of parameters in the general solution of AX is equal to 0? So the question is, what is the maximum number of parameter, that means free variable, in the general solution of AX is equal to 0? In the general solution of AX equal to 0. Okay, here the A is 7 by 4, so the X is 4 by 1, and this is the O of R7. Okay, so we know that the number of parameters in the general solution of this equation is exactly the nullity of A. So I'm going to use this one. We have the rank of A plus nullity of A is equal to 4. Okay, so we have rank of A plus nullity of A is number of columns of A. In this case, we are dealing with 7 by 4, so it's equal to 4. So I'm using, again, this equality here. So that means, this tells me that the nullity of A is equal 4 minus rank of A. If I would like to maximize this number because of this sign minus here, I need to minimize the rank of A. And the minimum value of rank of A is 0. So that means the maximum value of nullity of A will be 4. Okay, this one will be 4. So the minimum value for rank of A is 0. So the maximum value for the nullity will be 4. The maximum value. And exactly we have equality. That means nullity of A is equal 4 if and only if A is the 0 matrix. Okay. Another remark again here You see, I'm insisting on those points because I want you to think about those questions in different ways. I wrote it for you, x is in 4 by 1. That means the solution to this equation, homogeneous equation, ax is equal to 0, they are in R4. So the null space of A is a subspace of R4. So the dimension of the null space, that means the nullity of A cannot exceed 4. And it is equal to 4. That means it is equal to the whole vector space R4 when A is equal to 0. So N of A is a subspace of R4. And so the dimension and so dimension of N of A, which is by definition the nullity of A, will be less or equal dimension of R4, which is equal to 4. And if dimension of the null space, that means the nullity of A, is equal exactly to 4, that means the null space is equal to the whole vector space R4, and this is true only when A is the zero matrix, because if A is the zero matrix, then no matter what you put x here, A times x will be 0. Okay, this is what's gonna correspond to what's written here in between these parentheses. The nullity is equal to 4. That means the whole null space, your null space is the whole vector space R4, if and only if this is true when A is the zero matrix. Okay. Now I will finish this section by the following trees. And this tree is a tree of equivalent statement, but we have the proof of all of them, so I'm just gonna write it down. Okay, so, but I'll put very important. Okay, very important. So I'm gonna put a tree of statements that are equivalent to each other. Okay, first of all, whatever I'm gonna write here works only for square matrix. Okay, so let A be a square matrix. So, and I'm gonna take its size n by n. A is n by n matrix. Okay. So we have seen similar, by the way, we have seen similar tree like this of equivalent statement in chapter 1, and I think also in chapter 2. So we're gonna just add a few important equivalent statements that now we figure out through those previous sections. 4.4, 4.5, 4.6, and now 4.8. Okay, so A is invertible. We know that if this is invertible, if the matrix A is invertible, this is equivalent to say that the homogeneous system AX is equal to the 0 of Rn has a unique solution. Which is the trivial solution. But A is invertible means the columns of A are linearly independent. but A has n columns, and each column is in Rn. So I have n vectors in Rn that are linearly independent. So that means they are going to form a basis for Rn. So I can say the columns of A form a basis for Rn. Remember, each column is in Rn. So, in Rn. How many of them? I have n of them. N vectors in Rn that are linearly independent. They will form automatically a basis. And so, what will be the column space of A? Well, the column space is by definition spanned by the columns of A, but if you tell me the columns of A form a basis of Rn, then the column space of A is exactly Rn, the whole vector space. The same here, because A is invertible, I can say that this one is also equivalent to say the same statement is true for the row space. If I do it for the column space or for the row space, it's the same. The rows of A are linearly independent. But each row is in Rn. These guys, the row of A in Rn. How many of them? I have n rows. So n rows in Rn, and they are linearly independent, then they will form a basis for Rn. Form a basis for Rn. And so, again, a similar argument here. The row space of A will be Rn. Now, what is the rank of A? The rank of A will be n. So what will be the nullity of A? Nullity of A, dimension of the null space will be 0, but you can see it from here also. And that gives me that nullity of A is 0, because the null space of A is reduced only to the O vector of Rn, which is, we call the trivial subspace, which is the subspace containing only the O vector. So this is what I find important with respect to what we have seen in section 4.8 and 4.7. This is the important tree of those equivalent statements. So I will stop here, and I want to say that we are done with chapter 4. The section 4.9 and 4.10 we will keep it for chapter 8. The chapter after chapter 4, if you go back to the syllabus, you will see chapter 8. So section 4.9 and 4.10, which is about a matrix transformation, will be seen later in chapter 8. It is really a very special case of linear transformation. So no need to do it for this chapter. We will do it in chapter 8. And the chapter 8, with respect to the syllabus, is exactly the chapter after this one, after chapter 4. But for now, chapter 4 is done. The last section I want you to focus is the section 4.8. Thank you very much. We will upload this video for you very soon.